Welcome to our short discussion of a simple pendulum. We're going to be looking at an idealized model. We're going to assume that the mass is concentrated at one single point. It means that this string that is shown here is unstretchable, it has no weight, and it's also in a uniform gravitational field. And so when we pull it a little bit to the side, and you'll notice that this angle here is very, very small. It has to be basically about 10-15 degrees or less. It starts to oscillate back and forth. And so if you were to look at its motion along the x-axis, it would be simple harmonic motion. So lots of examples of things in nature that are like simple pendulums, like just simply maybe a wrecking ball on a crane, or maybe a child just swinging back and forth on a swing. There are a number of ways to derive this, so I'm just going to show you one way to look at it. If we look at this object here at the end point and draw the forces acting on it, we have the tension and the weight acting on it. And so we're going to be looking at its position along the x-axis here, and we're going to be looking at its acceleration along that axis defined here. So we're going to take the x component of that tension, which is Ft sine theta, as the sum of the forces, and that's going to be producing a net force of ma along the x-axis. Okay, and then we look at sine theta, and sine theta, if you look at this little triangle in here, is the opposite over the hypotenuse, so it's this distance x divided by the length of the string. So we're going to replace sine theta with x over L, so now we have the tension times the position x all over L. Now, the tension is then approximately written down as mg. Why is that so? Well, if we look along the y-axis, the sum of the forces in the y should be 0. And so really it should just be the y component of that tension is equal to mg, but if the angle is quite small, that's about 10 degrees or less, we're going to find that cos theta is approximately 1, and so we can say that the tension is approximately mg. So it's a small angle approximation that we're using. So we now replace Ft with mg, and we see that the mass now on both sides will cancel out, and we have g over L times x equals ax. And we recall before we learned that a as a function of time is equal to negative the angular frequency squared times the position as a function of time. So really, this angular frequency squared, once again, is now shown for a simple pendulum to be g divided by L. L is the length of the pendulum, and g is the acceleration due to gravity. You'll notice that there is no mass in our equation because the mass cancels out. So the mass of the pendulum is irrelevant. So we see that the angular frequency squared is equal to g divided by L. So therefore the angular frequency is the square root of that. And we also know that the angular frequency is equal to 2 pi times f, or 2 pi divided by t. So if we set that equation equal to 2 pi divided by t and rearrange for t, we get the following equation for the time to make one complete oscillation back and forth. It is equal to 2 pi times the square root of L over g. So longer pendulums will have a longer period, and shorter pendulums will have a shorter period. And also the acceleration due to gravity. If you go into a weaker gravitational field, such as the moon, then you'll find the period will be a lot longer. I should also emphasize once again that the motion of the pendulum is only approximate for simple harmonic motion. So this is only going to work for basically angles that are less than 15 degrees. All right, even at 15 degrees, the value that this would predict is about 0.5% off. It's a little less, 0.5% less than it actually is. All right, so now go ahead and try the next example and see if you understand the simple pendulum.